In the autumn of 2019, telescopes across Earth turned their electronic eyes toward a faint smudge of light moving against the star field of Lynx constellation. The object bears the designation Trojan Atlas, marking it as only the third confirmed visitor from beyond our solar system's gravitational embrace. It tumbles through space in a slow, hypnotic rotation, catching and releasing sunlight like a cosmic lighthouse whose beam sweeps across millions of kilometers of emptiness. The Roman numeral I stands for Interstellar, a simple designation that carries the weight of profound isolation. This wanderer has spent eons drifting between star systems, carrying whatever stories it holds through the galaxy's patient darkness. The constellation Lynx spreads across northern skies like a faint celestial pathway, its stars forming patterns that ancient astronomers imagined as a wild cat stalking through stellar territory. Against this backdrop, 3 Atlas moves with the deliberate pace of geological time, its motion barely perceptible to instruments that must track its position over days and weeks to confirm its trajectory. The object's discovery emerges from the intersection of human curiosity and electronic patience. Automated systems that scan the same patches of sky night after night, accumulating photons like cosmic archaeologists gathering evidence of distant worlds. This cosmic drifter carries no radio beacon, no obvious signs of artifice. Yet something about its presence stirs questions that reach beyond simple astronomy. Its trajectory speaks of origins in stellar neighborhoods where our sun's light has never reached, where alien physics shaped alien worlds under alien skies. Only took 4.5 billion years for something this mysterious to visit our particular corner of the galaxy. The universe maintained its silence for so long, and now offers this single messenger, wrapped in ice and shadow, tumbling through our inner solar system like a message in a bottle cast into an ocean of stars. Each photon reflected from its surface carries information encoded during its formation, spectroscopic fingerprints that speak of temperatures and pressures that existed in stellar environments whose chemistry followed different evolutionary paths. The object's discovery emerges from the patient work of sky surveys, automated telescopes that photograph the same patches of sky night after night, searching for anything that moves against the fixed stars. These robotic sentinels scan the heavens with electronic patience, accumulating terabytes of data that capture the slow dance of celestial mechanics. The Asteroid Terrestrial Impact Last Alert System, whose acronym gives 3i Atlas part of its name, operates from observatories in Hawaii and South Africa, its wide-field cameras designed to detect potentially hazardous objects approaching Earth. When 3i Atlas appears in their images, it registers as little more than a streak of pixels, a ghost impression left by photons that travelled across the void for millions of years only to strike silicon sensors on a small blue world. The light that reveals its presence began its journey when Earth was a different planet entirely, when continents held different shapes and oceans carried different chemistry. During the object's long voyage through interstellar space, our planet experienced ice ages and warm periods, witnessed the rise and fall of species, felt the gradual reshaping of its surface by water and wind and tectonic forces. Mountains rose and eroded while 3i Atlas maintained its steady trajectory through regions of space where the sun appears as merely another star among countless others, where Earth remains invisible even to the most powerful telescopes. Astronomers calculate its path with the precision of celestial mechanics, mapping its hyperbolic orbit through the inner solar system. The mathematics reveal a visitor that will make its closest approach to Earth and then continue outward, never to return. It follows gravitational laws written in the language of space-time, indifferent to the curiosity it generates among the observers watching its passage from their spinning planet. Its orbit curves around our sun like a gentle question mark, a cosmic punctuation that asks what stories wait in the spaces between stars. The calculations show it moving at speeds that speak of deep time and vast distances, carrying momentum accumulated across galactic neighborhoods where ice forms differently and starlight tastes of foreign elements. The trajectory analysis requires sophisticated computer models that account for the gravitational influences of all major solar system bodies. Jupiter's massive presence bends the visitor's path slightly, while the Sun's gravity provides the dominant force that curves its hyperbolic arc. These calculations trace the object's future course beyond Neptune's orbit, where it will gradually fade from telescopic view and resume its journey through the galaxy's disk. Only took one brief encounter with our solar system's gravitational architecture for humanity to measure and catalogue this ambassador from stellar distances. This quiet testimony to planetary formation processes that operated under different stellar conditions. The mystery deepens with each observation. Unlike the rocky asteroids and icy comets native to our solar system, 3I Atlas displays characteristics that challenge easy categorization. Its spectroscopic signature hints at compositions unknown in local space, materials that could only have formed in the stellar nurseries of distant suns. Spectroscopes split its reflected light into component colors, revealing absorption lines that tell stories of formation processes alien to our familiar solar chemistry. The patterns speak of temperatures and pressures that existed in stellar systems whose names appear only as catalogue numbers, whose planets, if they ever existed, completed their geological stories under different constellations. Ground-based observatories track its motion with the dedication of cosmic archaeologists, measuring subtle changes in brightness that reveal its tumbling rotation. Each variation in luminosity offers clues about its shape and surface properties, creating a puzzle that assembles itself one photon at a time. The object rotates with a period measured in hours, presenting different faces to the warming touch of solar radiation as it continues its ancient journey through the inner planet's domain. Photometric measurements reveal an elongated shape, perhaps several times longer than it is wide, tumbling end over end as it travels. Only took millions of years of wandering for it to happen upon our neighborhood, where patient humans wait with instruments capable of reading stories written in reflected starlight. Radio telescopes join the vigil, their massive dishes turning toward the visitor like flowers following the sun. They listen across frequencies where artificial signals might hide, searching for patterns that would distinguish technology from nature. The electromagnetic spectrum holds spaces where intelligence might choose to broadcast, wavelengths that penetrate interstellar dust and carry efficiently across galactic distances. Hydrogen atoms throughout the galaxy emit radiation at a characteristic frequency, creating a universal background hiss that any technological civilization would recognize. Yet 3I Atlas maintains its silence, offering only the whisper of thermal radiation expected from any cold body warming slightly in the sun's embrace. If it carries messages, they remain encoded in languages of ice and rock rather than radio waves and mathematics. The search for artificial signals represents humanity's first attempt to eavesdrop on possible communications from interstellar space, listening for the electromagnetic fingerprints that might betray technological origin. Radio astronomy has spent decades searching for such signals from distant stars, but 3 Atlas offers the first opportunity to examine a physical object that demonstrably originated beyond our solar system. This silence speaks as eloquently as any signal might, suggesting either natural origin or technologies that operate beyond human understanding of communication methods. The visitor's strange geometry reveals itself through patient observation, each rotation period offering glimpses of an object that defies the familiar categories of solar system debris. Telescopic measurements suggest an elongated form, perhaps 10 times longer than its width, tumbling through space like a cosmic cigar or needle threading its way between planetary orbits. This unusual aspect ratio distinguishes 3I Atlas from the roughly spherical asteroids and potato-shaped comets that populate our local gravitational neighborhood, hinting at formation processes that operated under different physical constraints. The object's tumbling motion follows no simple pattern, its rotation axis precessing through space as gravitational forces and thermal effects subtly influence its angular momentum. Advanced computer models attempt to reconstruct its three-dimensional shape from the changing light curves, building mathematical sculptures that exist only in digital space. These reconstructions suggest a body stretched by forces unknown, perhaps the remnant of a larger structure that fragmented during its ejection from its parent stellar system. Only took millions of rotations during its interstellar journey for thermal cycling and cosmic ray bombardment to weather whatever surface features once marked its origin. Photometric analysis reveals brightness variations that speak of surface irregularities, perhaps impact craters or compositional differences that create patterns of light and shadow as the object spins. Each measurement point represents thousands of photons gathered by telescope mirrors, their collective message assembled into curves that map the visitor's changing profile against the stellar background. The data accumulates like sedimentary layers in an electronic core sample, preserving moments of reflected sunlight that carry information about surface properties shaped by processes that operated in stellar environments humanity has never directly observed. The tumbling period suggests internal structure more complex than a simple rubble pile held together by weak gravitational forces. Solid objects maintain rotation stability differently than loose aggregations of debris, their moments of inertia reflecting mass distributions that encode stories of formation and subsequent modification. If 3I Atlas consists of consolidated material rather than loosely bound fragments, it survived whatever catastrophic event ejected it from its birth system with structural integrity intact. The mathematics of rotational dynamics reveal constraints on density and internal composition that narrow the range of possible formation scenarios. Thermal infrared observations attempt to measure how efficiently the object absorbs and radiates solar energy, providing clues about surface composition and texture. Dark materials absorb more heat than reflective surfaces, while porous structures retain thermal energy differently than solid rock or ice. The balance between absorbed sunlight and radiated heat creates temperature maps that exist only in the infrared portion of the electromagnetic spectrum, invisible to human eyes but readable by instruments designed to sense the gentle warmth of objects in space. These thermal signatures suggest surface materials that formed under stellar conditions different from those that shaped our familiar asteroids and comets. The object's albedo, or reflectivity, measures only a few %, indicating a surface darker than charcoal that absorbs most incident light. This low reflectivity resembles carbonaceous asteroids found in our outer solar system, but spectroscopic analysis reveals absorption features that don't match any known meteorite classes. The darkness speaks of organic compounds or complex minerals that formed in environments where carbon chemistry proceeded along pathways alien to terrestrial experience. Only took eons of cosmic ray exposure to darken whatever surface materials originally reflected light from its parent star. creating a patina of radiation damage that obscures the visitor's original appearance. Ground-based adaptive optic systems struggle to resolve details on an object whose apparent size barely exceeds the theoretical resolution limits of Earth's largest telescopes. Atmospheric turbulence blurs the already tiny image, requiring sophisticated computer processing to extract meaningful information from distorted photons. Each observation session represents a collaboration between human ingenuity and natural physics, using laser guide stars and deformable mirrors to compensate for the churning motions of Earth's atmosphere. The resulting images remain frustratingly small, showing 3 Atlas as little more than a point source that varies in brightness as it rotates. Space-based telescopes offer clearer views, their instruments operating above the atmospheric veil that complicates ground-based observations. The Hubble Space Telescope pivots to track the visitor's motion, its mirrors gathering light uncontaminated by terrestrial weather or atmospheric absorption. These observations reveal subtle details in the object's light curve, confirming the elongated shape suggested by ground-based measurements, while providing more precise estimates of rotation period and axis orientation. The clarity of space-based photometry allows astronomers to distinguish between different models of internal structure and surface composition. Radar attempts to illuminate the object with powerful transmissions from Earth's largest radio telescopes fail to return detectable echoes, suggesting either a surface composition that absorbs radio waves efficiently or an orientation that scatters reflected signals away from terrestrial receivers. Radar astronomy has successfully mapped the surfaces of near-Earth asteroids in extraordinary detail, revealing boulder fields and crater rims with resolution measured in meters. The silence from 3I Atlas denies astronomers this detailed reconnaissance, leaving its surface topography to imagination and mathematical modelling. Perhaps its composition includes materials that absorb radio frequencies, or its tumbling motion presents no surfaces perpendicular to Earth-based transmissions during the brief window of opportunity. Polarimetric measurements analyze how the object's reflected light becomes preferentially oriented in specific planes, providing information about surface texture and composition that remains invisible to conventional photometry. Smooth surfaces polarize light differently than rough terrain, while different minerals impose characteristic signatures on reflected photons. These subtle measurements require precise instruments and careful data analysis, extracting information encoded in the electromagnetic field orientations of individual photons. The polarization patterns suggest surface properties unlike those found on familiar solar system objects, hinting at formation or modification processes that operated under different physical conditions. The visitor's apparent magnitude changes not only with its rotation, but also with its distance from Earth and the Sun, following predictable patterns that allow astronomers to separate intrinsic brightness variations from geometric effects. As 3I Atlas approaches its closest distance to our planet, it appears brighter simply because more of its reflected light reaches terrestrial telescopes. Simultaneously, its changing angle relative to the Sun creates phase effects similar to lunar phases, though much more subtle due to the object's irregular shape and low reflectivity. These overlapping variations require careful mathematical separation to reveal the underlying rotation period and surface properties. The object's trajectory carries it through regions of interplanetary space, where dust particles and charged particles from the solar wind create a tenuous environment that may slightly modify its surface properties during its brief visit to our stellar neighborhood. Solar radiation pressure exerts gentle forces that could alter the rotation of small objects, while thermal cycling as the visitor warms in approaching sunlight might cause surface materials to expand and contract, in ways that affect light scattering properties. These subtle influences represent the first significant environmental changes 3 Atlas has experienced in millions of years, marking its transition from the cold emptiness of interstellar space to the warmer embrace of our sun's radiation. Spectroscopic analysis reveals the visitor's surface catching starlight in wavelengths that speak of ancient ice and organic compounds, materials that could only survive the journey between stars wrapped in protective darkness. The object's spectrum displays absorption features characteristic of water ice mixed with carbon-based molecules, creating a chemical fingerprint that tells of formation in regions where stellar radiation never penetrated deeply enough to drive away volatile materials. These frozen compounds preserve records of the interstellar medium through which 3I Atlas wandered, accumulating thin layers of cosmic dust and gas during its million-year journey through the galaxy's sparse regions. The spectral signatures emerge from sophisticated instruments that split reflected sunlight into component wavelengths, revealing the molecular absorption lines that identify specific chemical species on the visitor's surface. Water ice creates characteristic dips in the infrared spectrum, while organic compounds produce complex patterns that require comparison with laboratory measurements of similar materials subjected to space-like conditions. Each absorption feature represents countless molecular vibrations responding to incident photons, creating a chorus of chemical identification that resonates across the electromagnetic spectrum. Only took eons of cold storage in interstellar space to preserve these delicate compounds in pristine condition, protected from the destructive radiation that would have driven them away in the inner regions of any stellar system. The presence of carbon-based molecules suggests either primitive organic chemistry that preceded biological processes or the remnants of more complex materials that survived the catastrophic ejection from their parent world. Spectroscopic databases built from decades of laboratory work and meteorite analysis provide templates for identifying these interstellar hitchhikers, though many of the absorption features remain unmatched by any known terrestrial or solar system materials. The chemistry speaks of formation environments where carbon and oxygen combined under temperature and pressure conditions that existed in stellar nebulae, whose light has long since faded from the galactic neighborhood. Infrared observations reveal thermal emission patterns that vary with the object's rotation, suggesting uneven distribution of materials across its surface. Some regions emit more efficiently than others, indicating compositional differences that create a patchwork of thermal properties invisible to optical telescopes but clearly readable in the heat radiation spectrum. These thermal maps exist only in the infrared realm, where temperature differences of a few degrees translate into measurable variations in emitted photons. The pattern suggests surface features that formed through processes unknown in our solar system, perhaps impact craters filled with different materials or exposed layers that represent geological stratigraphy from an alien world. The detection of complex organic molecules challenges models of how such materials survive exposure to cosmic radiation during interstellar travel. High-energy particles streaming through the galaxy gradually break down complex chemical structures, reducing organic compounds to simpler forms over timescales measured in millions of years. Yet 3 Atlas displays spectral evidence of molecules that should have decomposed during its journey, suggesting either more recent formation or protection mechanisms that shielded vulnerable chemistry from radiation damage. Perhaps the object's interior harbors a reservoir of pristine materials beneath a radiation-weathered surface layer, preserving chemical fossils from its origin world in a cosmic deep freeze. Ground-based spectrographs track subtle changes in absorption features as different portions of the object's surface rotate into view, mapping chemical variations across its elongated form. Each spectrum represents light gathered over minutes or hours, averaging the contributions from whatever surface materials happen to face Earth during the observation period. The changing spectral features suggest heterogeneous composition, with some regions richer in ice and others dominated by rocky or organic components. This chemical geography tells stories of formation processes that created distinct terrains, perhaps through impact mixing or thermal segregation, during the object's original accretion in its parent stellar system. The visitor's low albedo becomes more mysterious when combined with its spectroscopic properties. Since pure ice should reflect sunlight efficiently rather than absorbing most incident photons, the darkness suggests either contamination by carbon-rich materials or modification by space-weathering processes that gradually darken surfaces exposed to cosmic radiation. Solar system comets display similar darkening effects as repeated approaches to the Sun drive away bright ice and leave behind refractory residues that absorb light efficiently. Yet 3I Atlas shows no evidence of active outgassing that would indicate volatile sublimation, maintaining its spectral features without the dramatic changes that characterize active comets in our neighborhood. Polarimetric spectroscopy combines light polarization measurements with wavelength analysis, providing additional constraints on surface texture and mineral composition that remain invisible to conventional instruments. Different materials impose characteristic polarization signatures on reflected light, while surface roughness affects how efficiently various wavelengths become preferentially oriented. These measurements require extraordinarily precise instruments capable of detecting polarization changes that represent fractions of a percent variation in the electromagnetic field orientations of individual photons. The resulting data suggests surface materials with optical properties unlike any catalogued meteorite classes, hinting at formation under stellar conditions that never occurred in our solar system. Laboratory experiments attempt to reproduce the spectral characteristics observed in 3I Atlas by subjecting various ice and rock mixtures to conditions that simulate interstellar space. Researchers create synthetic materials in vacuum chambers, cooled to temperatures approaching absolute zero, then irradiate them with particles and ultraviolet light to mimic cosmic weathering effects. The resulting spectra provide comparison templates for interpreting the visitor's observed properties, though many features remain unmatched by any laboratory analogues. Only took decades of careful experimentation to build libraries of spectral signatures. Yet 3I Atlas displays chemical fingerprints that extend beyond current understanding of space weathering and organic chemistry preservation. The object's thermal infrared spectrum reveals emission features that correspond to silicate minerals common in rocky asteroids, suggesting a mixed composition that includes both volatile and refractory materials. This combination resembles cometary nuclei found in our outer solar system, where rocky frameworks provide structural support for ice and organic compounds accumulated during formation in the cold regions beyond Neptune's orbit. Yet the specific mineral signatures differ subtly from familiar solar system compositions, displaying crystalline structures that formed under different temperature and pressure histories. These silicate fingerprints preserve records of condensation processes that operated in stellar environments with different elemental abundances and thermal evolution patterns. Near-infrared spectroscopy searches for absorption features that would indicate the presence of complex organic molecules or even amino acids, the building blocks of terrestrial biochemistry. While no definitive biosignatures appear in the data, the spectra display broad absorption features consistent with large organic molecules that resist easy identification through comparison with laboratory standards. These materials might represent the chemical precursors to biological processes, organic compounds that formed through non-biological chemistry but could serve as raw materials for life under appropriate conditions. The detection of such molecules in an interstellar visitor raises questions about how widely the ingredients for biology distribute through the galaxy's planetary systems. The spectroscopic evidence accumulates like testimony from a cosmic witness that observed stellar chemistry under conditions humanity has never directly encountered. Each absorption line represents molecular interactions that occurred in environments where different physics shaped the building blocks of worlds, where ice formed from water vapor that condensed in stellar winds carrying exotic isotopic ratios. The object's surface preserves a chemical library written in wavelengths of light, encoding information about formation processes that operated millions of years ago in stellar neighborhoods whose names exist only in astronomical catalogues. Only took one chance encounter with our solar system for terrestrial instruments to read these alien spectral signatures, translating photons into stories of distant chemistry. The mathematics of exile reveal themselves through orbital calculations that trace 3 Atlas backward through millions of years, following gravitational breadcrumbs across the galaxy's slowly rotating disk. Computer simulations run in reverse, unwinding the object's trajectory through encounters with stellar neighborhoods where massive stars completed their life cycles and planetary systems rose and fell, while this messenger wandered between destinations that shift positions across cosmic time. The calculations paint portraits of ejection events that scattered planetary debris across interstellar space, with velocities sufficient to escape their parent star's gravitational embrace forever. Celestial mechanics provides the mathematical language for reconstructing the visitor's deep history, using current position and velocity measurements to extrapolate backward through the complex gravitational landscape of our galactic neighborhood. The equations account for the Sun's motion through space, the galaxy's differential rotation, and the gravitational influences of nearby star systems that might have deflected the object's path during its interstellar journey. Each calculation represents a collaboration between observational precision and theoretical physics, translating telescope measurements into trajectories that span geological timescales. The orbital analysis suggests 3I Atlas originated from a stellar system located roughly 400 light-years from our current position, though the galaxy's rotation has since carried both the visitor and its source region to different locations in the galactic disk. During the object's estimated travel time of several million years, stellar motions have scattered the original neighborhood across hundreds of light-years, making precise identification of its parent system virtually impossible. Only took a few million orbits around the galactic center for all the players in this cosmic drama to assume completely different positions, like actors leaving a stage after the performance has ended. Galactic dynamics complicate the backward trajectory calculations, since stars move through space at different velocities depending on their positions relative to the galaxy's spiral arms and central bulge. The Sun participates in this grand celestial choreography, completing one orbit around the galactic center every 200 million years while oscillating up and down through the disk plane like a cosmic carousel horse. During 3I Atlas's journey, both the visitor and our solar system traced complex paths through regions of space, where stellar densities and gravitational influences varied with location and time. Statistical analysis of the trajectory calculations yields probability maps that highlight regions where the object most likely originated, painting broad swathes of the galactic disk in shades of mathematical likelihood. These maps identify stellar populations that could have hosted planetary systems capable of ejecting debris with the appropriate velocities and directions to reach our neighborhood after millions of years of travel. The analysis favors regions where massive stars underwent supernova explosions, or where close binary systems disrupted planetary formation through gravitational chaos. Yet the uncertainty bands remain large enough to encompass thousands of stellar systems, making definitive source identification impossible with current observational precision. The energy requirements for ejecting planetary material at interstellar velocities constrain the types of events that could have launched 3I Atlas on its galactic journey. Gravitational slingshot encounters with massive planets can accelerate smaller objects to escape velocity, while stellar explosions or close passages between binary stars can scatter debris across much larger velocity ranges. Computer models simulate these ejection mechanisms, calculating the distribution of velocities and directions that result from different catastrophic scenarios. The visitor's current trajectory falls within the predicted ranges for several possible ejection events, though distinguishing between different mechanisms requires additional observational constraints. Close encounters with other stars during the object's interstellar passage could have modified its trajectory in ways that obscure its original ejection, velocity and direction. The galaxy contains numerous stellar systems that passed within light years of 3I Atlas's path during the past few million years, each representing a potential gravitational deflection that complicates backward trajectory calculations. Monte Carlo simulations explore thousands of possible encounter scenarios, mapping how small gravitational perturbations accumulate over millions of years to create large uncertainties in reconstructed origins. Only took a few chance encounters with passing stars to erase precise memory of the visitor's birth circumstances, replacing certainty with probability distributions that span vast regions of space. The object's hyperbolic orbit through our solar system carries excess velocity that speaks of its interstellar origin, moving too fast to have formed within our Sun's gravitational domain. This orbital energy represents kinetic inheritance from whatever ejection event launched it across the galaxy, modified by subsequent gravitational encounters and the galaxy's large-scale dynamics. The mathematics of orbital mechanics allow astronomers to subtract the Sun's gravitational influence and calculate the visitor's velocity relative to the local standard of rest, the reference frame that accounts for our solar system's motion through the galactic neighborhood. Precision astrometry tracks tiny changes in the object's position against the stellar background, measuring proper motion that reflects its three-dimensional velocity through space. These measurements require telescopic precision approaching the limits of current technology, detecting positional shifts smaller than the apparent size of a coin viewed from thousands of kilometers away. Each measurement represents the culmination of decades of technological development in telescope design, detector sensitivity, and data analysis techniques. The accumulated observations provide velocity components accurate to within a few kilometers per second, sufficient to constrain models of galactic trajectories and ejection scenarios. The visitor's approach geometry suggests it entered our solar system from the direction of the constellation Gemini, emerging from interstellar space along a trajectory that brought it through the orbital plane where planets concentrate their gravitational influences. This approach angle maximizes the deflection effects of Jupiter and Saturn, whose massive gravitational fields bend the visitor's path while providing opportunities for detailed observation as it passes through the inner solar system. The geometry represents a fortunate coincidence that places 3I Atlas within range of Earth's most powerful telescopes during its brief transit through our stellar neighborhood. Dynamical models explore how the object's trajectory will continue after leaving our solar system, predicting its future path through the galaxy's gravitational landscape over the next several million years. The calculations show 3 Atlas resuming its journey through interstellar space, gradually slowing as it climbs out of the Sun's gravitational well, while heading towards stellar regions that currently lie hundreds of light-years away. Its future trajectory will carry it through parts of the galaxy, where star formation proceeds at different rates, and stellar populations display different characteristics, potentially encountering gravitational influences that will again modify its path through space. The mathematical reconstruction of deep time trajectories highlights the chaotic nature of galactic dynamics, where small uncertainties in initial conditions grow exponentially over millions of years to create large uncertainties in predicted outcomes. This sensitivity to initial conditions resembles weather forecasting on terrestrial timescales, where minor measurement errors propagate through complex systems to limit prediction accuracy beyond certain time horizons. In the case of Thruai Atlas, current observational precision allows backward trajectory calculations spanning several million years, but extending these models further into the past yields probability distributions too broad to identify specific source mechanisms or stellar systems. Radio astronomy searches for pulses along the visitor's reconstructed trajectory, using these cosmic lighthouses as navigational beacons that could provide independent confirmation of the object's path through interstellar space. Pulsars emit precisely timed radio signals that allow astronomers to measure distances and proper motions with extraordinary accuracy, creating a reference grid against which other objects' trajectories can be mapped. If 3i Atlas passed near any catalogued pulsars during its journey, timing observations might reveal gravitational deflections that occurred millions of years ago, providing additional constraints on the visitor's deep history. Yet the galaxy contains relatively few pulsars with timing precision sufficient for such archaeological astronomy, and most lie far from the object's probable trajectory. When stars die violently, they scatter the accumulated debris of planetary formation across galactic distances, creating populations of wandering orphans that drift through interstellar space like cosmic refugees from destroyed worlds. The death throes of massive stars release energies that dwarf planetary binding forces, accelerating rocky fragments and icy bodies to velocities sufficient for escape from their gravitational origins. Supernova explosions unleash the equivalent of billions of hydrogen bombs detonating every second for months, generating shock waves that propagate through stellar systems and strip away planetary atmospheres while hurling solid debris into the galaxy's sparse interstellar medium. The final moments of stellar evolution create conditions unlike anything experienced during the billions of years of stable nuclear burning that characterize main sequence lifetimes. When a massive star exhausts its nuclear fuel, gravitational collapse proceeds faster than the speed of sound through stellar material, creating core densities that exceed those found in atomic nuclei. The subsequent explosion releases more energy in seconds than our Sun will produce during its entire 10 billion year lifetime, creating temperatures and pressures that forge heavy elements, while simultaneously destroying the very planetary systems where those elements might have assembled into worlds. Computer simulations model these catastrophic events with equations that describe how matter behaves under extreme conditions, tracking shockwave propagation through stellar systems as expanding blast fronts encounter planets, asteroids, and comets. The calculations reveal complex dynamics where some objects experience complete vaporization, while others receive just enough energy to escape their star's gravitational influence without total destruction. This selective acceleration creates populations of ejected debris with a wide range of compositions and structural properties, from completely molten droplets that solidified during flight to intact rocky bodies that survived the violence with their original geology preserved. The physics of supernova shockwaves determines which materials can survive ejection into interstellar space, favoring dense, refractory objects that resist vaporization while eliminating more fragile structures that disintegrate under extreme heating. Rock and metal components endure better than ice and organic compounds, though objects ejected from outer planetary regions might retain volatile materials if they escape before the shockwave intensity peaks. The resulting population of interstellar wanderers represents a biased sample of pre-explosion planetary compositions, enriched in materials that could withstand the most violent stellar death mechanisms the galaxy produces. Binary star systems create additional scenarios for planetary ejection through gravitational chaos rather than explosive violence. When two stars orbit closely enough to exchange material, the resulting mass transfer can destabilize planetary orbits and scatter debris across interstellar distances through purely gravitational mechanisms. These gentler ejection processes preserve more delicate materials and complex structures, creating populations of wanderers that carry relatively pristine samples of their origin worlds. The dynamics of binary evolution span millions of years, allowing planetary systems time to develop complex geology and atmospheric chemistry before gravitational disruption sends fragments on journeys between the stars. White dwarf formation provides another mechanism for scattering planetary debris across galactic space when low-mass stars complete their evolution through gentler processes than supernova explosions. As these stars exhaust their nuclear fuel and shed their outer layers, the remaining white dwarf cores gradually cool, while their reduced gravitational influence allows planetary orbits to expand and occasionally become unbound. The planetary nebulae that mark this evolutionary phase create beautiful astronomical displays while simultaneously dispersing processed stellar material and planetary fragments across light years of surrounding space. The galaxy's spiral structure influences how ejected material propagates through interstellar space, with spiral density waves concentrating both stars and debris in regions where gravitational interactions occur more frequently. Objects ejected from stars in spiral arms encounter different environmental conditions than those launched from the quieter interarm regions, experiencing enhanced probabilities of gravitational deflection by passing stellar systems. These large-scale galactic dynamics create preferred pathways for interstellar debris, channeling wandering objects through regions where subsequent capture by other stellar systems becomes more likely. Stellar encounters during the galaxy's early history scattered planetary building materials across much larger distances than current ejection events. When stellar densities exceeded modern values by factors of hundreds or thousands, the primordial galaxy contained numerous massive stars that completed their evolution rapidly, creating successive generations of supernova explosions that processed and redistributed the heavy elements necessary for rocky planet formation. These ancient ejection events established the baseline population of interstellar debris that continues to wander through galactic space, gradually accumulating cosmic ray damage and interstellar dust coatings during journeys that span hundreds of millions of years. Gravitational wave astronomy opens new perspectives on stellar death mechanisms that could scatter planetary debris through previously unrecognized processes. The merger of neutron stars or black holes releases gravitational wave energy, while simultaneously generating kilonova explosions that forge precious metals and scatter them across interstellar distances. These exotic events occur less frequently than supernovae, but produce different elemental signatures that might be detectable in wandering debris that originated from systems disrupted by compact object mergers. Only took decades of technological development to detect gravitational waves directly. revealing stellar death mechanisms that remained hidden throughout the history of conventional astronomy. The survival probability for complex organic molecules during violent ejection events depends critically on the thermal history experienced during acceleration to interstellar velocities. Shockwave heating can drive chemical reactions that destroy biological molecules while creating new organic compounds through high-temperature synthesis pathways, unavailable under normal planetary conditions. Laboratory experiments attempt to reproduce these extreme environments, subjecting meteorite samples to shock pressures and temperatures comparable to those generated during stellar explosions. The results suggest that some organic materials can survive ejection events, while others undergo chemical transformations that create novel molecular species never observed in terrestrial environments. Impact excavation provides an alternative mechanism for launching planetary material into interstellar space through collision events that avoid the extreme temperatures associated with stellar explosions. Large asteroid or comet impacts can accelerate target materials to escape velocities while preserving temperature-sensitive compounds that would decompose during more violent ejection processes. The Chicxulub impact that ended the Cretaceous period launched Earth material at velocities approaching escape velocity, demonstrating how collision dynamics can scatter planetary samples across solar system distances. Scaling these mechanisms to larger impactors or lower escape velocities suggests pathways for gentle ejection that preserve complex chemistry during interstellar transport. Tidal disruption events occur when stellar systems pass close enough to massive objects like black holes or neutron stars to experience gravitational forces that exceed internal binding energies. These encounters can strip away outer planetary system components while leaving inner regions relatively undisturbed, creating populations of ejected debris with compositions that reflect the original radial distribution of planetary materials. The mathematical description of tidal forces reveals complex dynamics, where some objects gain energy, while others lose orbital momentum, leading to both ejection and capture scenarios that redistribute planetary building blocks across galactic distances. The chemical evolution of ejected materials during interstellar transport creates signatures that distinguish wandering debris from objects that formed within their current stellar neighborhoods. Cosmic ray bombardment gradually alters isotopic ratios and creates nuclear reaction products that accumulate over millions of years of exposure to galactic radiation fields. These space weathering effects serve as chronometers that record transport times, allowing astronomers to estimate how long objects have wandered between stellar systems. The accumulation of cosmogenic nuclides provides independent age constraints that complement dynamical models of orbital evolution and ejection scenarios. Statistical studies of stellar death rates and planetary system architectures allow astronomers to estimate the current population of wandering debris drifting through the galaxy's interstellar medium. The calculations suggest millions of objects larger than a few kilometers crossing through each cubic light-year of galactic space, with smaller fragments reaching number densities that approach those found in asteroid belts around active stellar systems. This invisible population of cosmic wanderers represents the accumulated debris from billions of years of stellar evolution, carrying samples of planetary compositions from throughout the galaxy's chemical evolution history. Only took recent advances in telescopic sensitivity to begin detecting these interstellar visitors directly, providing the first opportunities to study planetary materials that formed under different stellar conditions. The archaeology of dead worlds begins with the recognition that wandering objects like 3 Atlas might carry preserved traces of extinct civilizations, technological remnants embedded within ice and rock that survived ejection